Hello. In today's lecture, we will be looking at annular flow. In particular, we will look at an ideal case of annular flow where the interface is smooth and there is no, when the interface is smooth and the film thickness or the size of the core or the radius of the core is same throughout the channel. Okay. So, let us draw a configuration of a ideal annular flow. We have a channel, let us say this is a cylindrical channel, and in this cylindrical channel the interface is located somewhere here. So, this is phase 1. Let us consider gas liquid annular flow. So, gas is at the core and liquid is on the sides. Okay. And the radius of the channel is capital R, and the radius of the interface, let us name it as Ri, and we have properties of liquid rho L and rho G, and mu L and mu G are the density and viscosities of gas and liquid. Now, this configuration, when we look at the flow regimes in gas liquid flow in microchannels, we often encounter annular flow, but this is rarely the annular flow that we see in gas liquid flow in microchannels is rarely a smooth interface annular flow. We generally see the presence of waves on this annular flow, but to understand this, let us consider a case where for which we can obtain an analytical solution and can get a relationship, say for example, between pressure drop and film thickness or interfacial radius and the flow rate of the phases. So, this is the case that we are going to consider in this lecture. There can be annular flow, or what is termed as in general core annular flow for in the reference of liquid flow. So, there depending on the viscosities and densities of the two fluids plus hydrophobicity or hydrophilicity of the two liquids, one phase will be at the core and another phase will be these properties will determine which phase will be at the core and which phase will be near the wall. Okay. So, we are looking at this. We will use the terms for rho L and rho G or mu L and mu G. However, the same terms can be used with reference to liquid 1 and liquid 2. Okay. So, we will solve the mass conservation and momentum conservation equations, and because this is a cylindrical configuration, so we will prefer cylindrical coordinate system. So, where we have R, theta and Z. So, Z is this direction, R is the radial direction. And when we say that the flow is axisymmetric, that means there is no flow in the angular direction and no gradients in the angular or azimuthal direction. So, that means V theta is equal to 0 and del over del theta is 0. So, this is the symmetric configuration, axisymmetric configuration. At steady state, that means
the dou by dou t term is equal to 0.
Steady means, as you will know, that steady means the properties, the things, the configuration does not change with time. So all the variables with respect to time are constant. So that's why dou by dou t term in the conservation equations will be 0. Flow is laminar, and we do not need any models for turbulence. And we consider fully developed flow here. So when the flow is fully developed, we can say that del Vz over del Z is equal to 0. That means the velocity profile, whatever the velocity profile we obtain at one axial location, a similar velocity profile will be obtained at another location. So the corresponding difference delta V will be 0 or delta Vz will be 0. So the flow is fully developed, or that is the definition of a fully developed flow. Now let us write the conservation equations. So coming to the continuity equation, let us write the continuity equation in the cylindrical coordinate. So that is del rho by del t plus 1 over r del over del r rho Vr plus 1 over r del over del theta rho V theta plus del over del z rho Vz is equal to 0. Now because this is at steady state, so this term will be 0, and axisymmetric, so this term will be 0. Now what we have is del Vz over del z is constant because of fully developed flow. So this is because the flow is axisymmetric, and in this case this says that fully developed flow, so del Vz over del z is 0. The flow we consider in this case that the flow of both the phases is incompressible, so we can add the assumption of incompressible flow. So rho is constant in these cases, so that is why we can neglect this term. Now what we have from this, that del over del r of rho Vr is equal to 0, or V rho, this is rho r Vr, so we have rho r Vr, and that means r Vr is equal to a constant, and Vr is equal to constant over r, but Vr need to be finite. So at r is equal to 0, Vr is finite, so the term Vr will be 0. That means that is obvious from the flow configuration itself, because if the flow is happening in the radial direction, that means the interface radius will change, because the some flow will happen along this direction, and the radius, interface radius, will have to change to accommodate that flow. So because we do not have any such accelerational flow, so the radial component of velocity will be 0. So the only component of velocity that we have non-zero is Vz is non-zero, and Vr and V theta, they are 0. Okay. Now let us come to the R momentum equation. So for the cylindrical coordinate, the R momentum equation is rho
del VR over del T plus VR del VR over del R plus V theta over R del VR over del theta plus Vz del Vz over del Z minus V theta squared over R is equal to minus del P over del R plus mu del over del R 1 over R del over del R of R VR plus 1 over R square del 2 VR over del theta 2 plus del 2 VR over del Z2 minus 2 over R squared del V theta over del theta. We do not consider gravity, so we can say that the gravity effect is not considered. If we take horizontal flow, then the flow will not be axisymmetric if the gravity effect is considered. But remember that in micro channel, where the channel size is sufficiently small, the effects of gravity are anyway negligible. So now we can neglect, or we can strike out the terms which are not relevant for this. This is at steady state, so this term will be 0. VR is 0, so this term is 0. V theta is 0, so this is 0. Del Vz over del Z is 0, so this is also 0. And V theta is 0, so this is 0. And because VR is 0, so this term is 0. This is again 0 because of VR, same. And this is because V theta is 0. So what we have is del P over del R is equal to 0. That means P is not a function of R, or pressure is same at a particular cross section in the radial direction. So you take the pressure here and the pressure here, it is independent of the location. But remember, for the two phases, what these equations, we are writing general equation for phase 1 and phase 2, but when we consider the boundary conditions, we will have a pressure jump at the interface. So we will discuss that. But for a phase, inside one phase, the pressure is not a function of radius. Now for theta momentum term, what we have is rho del V theta over del T plus VR del V theta over del R plus V theta over R del V theta over del theta plus Vz del V theta over del Z plus VR V theta over R is equal to minus 1 over R del P over del theta plus mu del over del R 1 over R del over del R R V theta plus 1 over R squared del 2 V theta over del theta 2 plus del 2 V theta over del Z2 plus 2 over R square del VR over del theta. Okay. So in this again we neglect the terms. This term is 0, V theta is 0, so this term is 0, V theta is 0, V theta is 0, so all these terms are 0, and again we will have this is 0 because VR is 0, so we will have that pressure is not a function of theta. So that means pressure is, if it is, then it is a function of Z only. So let us look at the Z momentum equation, and when we write the Z momentum equation, rho del Vz over del T plus Vr del Vz over del R plus V theta over R del Vz over del theta plus Vz del Vz over del Z is equal to minus del P over del Z plus mu 1 over R del over del R R del Vz over del R plus 1 over R squared del 2 Vz over del theta 2 plus del 2 Vz over del Z2. While I have been very careful while writing these equations, I would request you to recheck these equations from a standard book. The book from which I have taken the equations is Transport Phenomena by Bird, Stewart and Lightfoot from the Appendix B. You can see all those equations are in the chapters where the Navier-Stokes equation have been derived. So again del Vz over del T because it is at steady state, and this term will be 0 because Vr is 0, this term will be 0 because V theta is equal to 0, and this term is 0 because del Vz over del Z is 0. Now this is 0 because gradient in theta direction are 0, and this is 0 because flow is fully developed, so del Vz over del Z and its derivatives are 0. So what we end up with is this minus del P by del Z is equal to mu 1 over R del over del R R del Vz over del R. So we will for clarity or for convenience we will assume that minus del P by del Z is equal to B. Note that this can be written now as minus dP by dZ because it does not depend, the pressure depends only on Z, so it is equal to the partial derivative is equal to the total derivative, and for Vz we will write as V only now onwards because for our convenience. Okay. So we can write this equation later on for both the phases. Let us look at the boundary condition. So the configuration we look at again. So this is our interface and the center. So at R is equal to capital R, which is channel wall, we will have V of liquid because this is liquid phase and this is gas phase. So VL is equal to 0. At R is equal to 0, which is at the axis, we will have V gas to be finite. So we will use this condition, or then we will also have at R is equal to Ri, which is at the interface. There are two boundary conditions: the velocity continuity so V liquid at R I is equal to V gas at Ri, and we will also have shear stress continuity mu L del VL over del Z at Ri is equal to mu G del Vg over del Z Ri. We will also have a boundary condition for normal stress, and that will be a jump in pressure. So we will have PL minus PG is equal to sigma kappa, and kappa is 1 over Ri in this case. So we can have sigma over Ri, but Ri is constant throughout, so we can say that dPL over dZ minus dPg over dZ is equal to 0. So that means, because Ri is not a function of Z, so that we can say that the gradients in both the phases are same, so we can have BL is equal to Bg from here. Now the equation, if we look at this equation again, mu over R, del over del R, R mu over R del over del R, R del V over del R is equal to minus del P by del Z, or dP by dZ, which we have named as B now. So we will have, when we integrate this equation, we will get del R of R del VR over del R is equal to BR over mu, which will give us this is not VR, del V over del R is equal to, this will be R and it will be equal to B R square over 4 mu. So we can write del V over del R is plus a constant of integration, let us say this at C1. So del V over del R is equal to B R over 4 mu plus C1 by R, and now we can write the same equation for gas and liquid phases. Using the shear stress continuity boundary condition at the interface, we will have mu gas del Vg over del R at Ri is equal to mu L del VL over del R at Ri. So if we substitute here, we will have 4 constants basically when we integrate this further. So we will have this term written for 2. So we will term these constants as C1L and C2L for 2 different things. So when we multiply by mu, we can have B Ri over 4 and mu will cancel out, plus mu G C1G divided by Ri. Similarly, we can write B Ri by 4 plus mu L C1L by Ri. So B Ri by 4, B Ri by 4 will cancel out, and what we will have as the boundary condition that mu G C1G is equal to, from this boundary condition we will get mu G C1G is equal to mu L C1L. Okay. So we have a relationship between the 2 constants for 2 phases, C1G and C1L. Okay. Now we can integrate this equation further. So we will have del V over del R is equal to BR over 4 mu plus C1 by R. When we integrate, we get V is equal to this will be BR by 2 mu. So when we integrate this further, we will have BR squared over 4 mu plus C1 ln R plus C2, and now we can write the same equation for gas phase and liquid phase. So if we use the boundary condition for gas phase at the axis at R is equal to 0, Vg is finite or defined. So then because ln 0 is not defined, so C1G has to be 0. So that means we have Vg is equal to BR square by 4 mu plus C2G. Okay, fine. So now we need to find out the constant C2G. Okay, for liquid phase, again we can write the same velocity profile. So if C1G is equal to 0, this will make C1L is equal to 0 too. So we will have VL is equal to B R square over 4 mu L plus C2L, and at R is equal to capital R, that is at the wall, we have VL is equal to 0. So we substitute 0 is equal to B capital R square by 4 mu L plus C2L, So by subtracting these two equations, we can get the velocity profile, or we can get rid of C2L. VL is equal to B over 4 mu L small r square minus capital R square. Now to obtain Vg, we will apply velocity continuity at the interface. That means VL at Ri is equal to Vg at Ri, and if we substitute that, we will get the liquid velocity we have already got. So the gas velocity we will get after substitution and manipulating the algebra, we will get Vg is equal to B over 4 mu gas small r square minus capital R I squared plus B by 4 mu L into R I square minus R square. So I request you to go through this step and do the required algebra. So we have got the velocity profile in the gas phase and velocity profile in the liquid phase for a smooth interface annular flow. Now once we have got that, then we can get the, by integration we can get the QL and QG. So QL will be integrating Vg 2 pi r dr from Ri to R, and Qg will be equal to 0 to Ri, sorry, this is VL, and Qg will be equal to Vg 2 pi r dr integrated from 0 to Ri. Now from this we can also find out the superficial velocities. So when we do the substitution, and the superficial velocity of the liquid phase will be QL over pi r squared. So 1 over pi r square, and Ug is equal to Qg over pi r square. So 1 over pi r square, and by substituting the values and do the necessary integration, we will get Ug is equal to minus B r square over 8 mu L into mu L over mu G minus 2 into Ri by R raised to the power 4 plus 2 Ri squared over R squared. Similarly, UL can be written as minus B R square over 8 mu L into 1 minus Ri squared over R square. So now in general, for any annular flow or for any experimental condition, in any experiment, what we will know is the gas and liquid flow rate. So if we want to obtain the velocity profile, the problem for us for the velocity profiles are that they are function of B, which is pressure gradient, and Ri, which is interfacial radius. Now we do not know both of these, so generally what we have QL and QG or UL, UG, these are the superficial velocities. So you can just note that UL, UG are superficial velocities. Are generally known for a flow. So by knowing this, we have two equations and we can solve equation, let us say A and equation B, to obtain B, which is pressure gradient, and Ri. So we can look at this in the ideal annular flow, these are the UL and UG, the two phase flow rates and the superficial velocities which we have just solved for. And now when we solve for pressure gradient and interfacial radius, so we can rearrange these two equations in such a manner that it becomes a quadratic equation in sigma IR square, sigma I square, where sigma I or xi I is equal to Ri by capital R. Okay, sorry, this is not sigma, this is psi, and so psi I is equal to Ri by R. So once we solve that, we can obtain what is psi I square, and from that we can obtain the roots of it. Generally, with my experience, I have observed that one root is always greater than 1. So we know that that is unphysical. So we will have to choose psi I with the condition that psi I is between 0 and 1. So we can get what is psi I, and when we substitute back in the pressure gradient, we will get the pressure gradient. So basically, by solving what we have done today is solve the ideal annular flow equation starting with basic Navier-Stokes equation. We have neglected the terms, the relevant terms in the r, theta and z system of equations and in the continuity equation, and finally after integrating we got the velocity profile which had 4 constants, 2 constants for the liquid phase and 2 constants for the gas phase. And then we had 4 boundary conditions. One is at the axis, that the velocity gradient should be finite and that ln it should be defined at the axis. Then we had 2 boundary conditions at the interface continuity and shear stress continuity, and 1 boundary condition at the wall, that the liquid velocity at the wall is 0. So by solving that, we could obtain the velocity profiles in terms of the pressure gradient and the interfacial radius. Once we have done that, then we integrated and obtained the flow rates of the 2 phases. Or from the flow rates, we can also obtain the superficial velocities, and by solving these 2 equations, we could get the pressure gradient and Ri or interfacial radius, so that we can get the velocity profile for any given gas and liquid phase flow rate. Now this ideal annular flow, there is a lot of literature on the stability analysis, non-linear and linear stability analysis of the annular flow. This is subject to different interfacial instabilities. So if you remember the capillary instability, which we discussed in the previous class, so in the capillary instability, a jet disintegrates into smaller droplets. So following that, the annular flow
is at lower velocities it becomes slug flow or Taylor bubble flow, and there are generally what we see in practice that there are always waves present at the interface, and that is because of probably the Kelvin-Helmholtz instability, which is that when there are two parallel liquid flowing, there are waves generated, or the small perturbations, they grow up to become wave to make the interface wavy. Okay, thank you.